Welcome. You're tuning in because you want the important stuff, quickly. No fluff. Just what you need to know about the events shaping our world.
And today, we're looking at something significant that might have flown under the radar a bit, a major power outage across Spain and Portugal recently.
Exactly. What went down, why, and maybe more importantly, what does it signal about our energy future? That's what we're digging into today.
Yeah, to help us understand this, we've been digging into Peter Zeihan's analysis, specifically from a recent video he put out. He's pretty good at breaking down these complex things, right?
He is. He gets into the technical weeds, but keeps it understandable. So our mission for this deep dive is to unpack this Iberian Peninsula blackout.
Figure out the root cause, why it happened in a place that's actually, pretty heavy on green energy.
And then look at the solutions, what can actually be done. So let's start at the beginning, the basics of how the grid even works.
Okay, so fundamentally, the issue revolves around alternating current AC power.
Right.
You can picture it like a wave, constantly going up and down, peaks and troughs.
Okay.
And this wave, this back and forth, happens at a really specific rhythm, a frequency. In Europe, that's 50 hertz, 50 cycles every second.
50 hertz. And in the US, it's 60, right?
Exactly, 60 hertz there. One isn't better than the other necessarily, but everything plugged into the grid in a region is built for that specific frequency.
So this frequency, this wobble, as Zeihan calls it, it has to be super stable, like a heartbeat.
Precisely. Dead stable. Because if that wobble gets erratic, if the frequency shifts, or worse, if you somehow get a second wobble interfering with the first, well, things go sideways fast.
Not fast. What happens to the equipment?
Electrical gear just isn't designed for that instability. It can start to shake itself apart, literally.
Yeah.
Overheat, catch fire, sometimes even explode. And the really stark thing here, Zeihan points out the Spanish outage, the whole destabilization, happened in about 4 seconds.
4 seconds. That's incredibly quick. It really shows how fragile the balance is. So what stops a small glitch from causing a total meltdown in just 4 seconds?
Well, the grid has protections, fail-safes. At key points, these nodes and interconnectors, there are systems designed to automatically disconnect if they detect that frequency going wild.
Like circuit breakers, but for the whole grid.
Kind of, yeah. It's a safety measure to stop damage spreading. But the problem in Spain, it seems, was the instability hit so hard and so fast across a wide area that the disconnections just cascaded. One cut off, putting strain elsewhere, causing another to cut off.
Exactly, a domino effect, leading to that widespread blackout.
Zeihan uses that analogy, right? The junior high dance. Everyone's doing the Macarena fine, that's the stable 50 hertz wobble. Then the DJ suddenly throws on the lambada. Total chaos. Different rhythm, nobody knows what to do.
It's a good way to picture it. Total system confusion. So what caused the music to change so abruptly in Spain and Portugal?
Right, what was the trigger? Well, this is where it gets interesting. It wasn't something added so much as something missing, a stabilizer. And it's directly linked to their big push into renewables.
Okay, how so? What's the traditional stabilizer?
Historically, that steady 50 hertz rhythm, that stable wobble, it's been maintained largely by good old-fashioned physics, specifically the kinetic energy stored in the huge spinning turbines of coal and natural gas power plants.
Okay, wait. So these plants aren't just making power. The fact that they have these massive spinning parts is actually helping keep the whole grid steady, like a giant flywheel.
That's a perfect analogy, exactly like a flywheel. These turbines are incredibly heavy, spinning really fast. They store a ton of rotational energy inertia.
Right.
So if the grid frequency starts to wobble a bit, dips or surges, operators can tweak the input to those turbines, more steam, less gas, whatever, speed them up slightly, slow them down slightly.
And that physical inertia resists the change. It gives them time to react.
Precisely. It acts as a buffer. It smooths out the bumps and gives the system crucial seconds to correct itself before things get out of hand.
Okay, that makes sense. So what was different during the blackout in Spain and Portugal? They didn't have enough of these spinning turbines online.
That seems to be the core issue identified in the analysis. At that specific time, something like 80% of their electricity was coming from solar and wind.
80%? That's a huge number for renewables.
It is a real achievement, environmentally speaking. But here's the technical catch. Solar panels and wind turbines, they generate direct current, DC.
Right, not the EC the grid uses.
Correct. So you need electronics, these things called inverters, to convert that DC into AC and crucially to match that 50 hertz wobble perfectly.
Okay, and the problem is these inverters don't have giant spinning parts inside them.
Exactly. Solar panels are static. Wind turbines spin, yes, but they connect through power electronics, the inverters. There are no massive, heavy turbines directly coupled to the grid frequency in the same way as a thermal plant.
So no significant kinetic energy storage. No flywheel effect.
Pretty much none in comparison. So when that wobble started, for whatever initial reason, maybe a sudden change in load or generation somewhere, there just wasn't enough of that traditional spinning inertia from coal and gas plants online to cushion the blow.
There was nothing to absorb the shock.
Right. Nothing to provide that buffer, that reaction time. And as Zan describes it, within those 4 seconds, without that stabilizing inertia, the system just collapsed.
So it's like the grid became much more brittle in a way, more susceptible to sudden shocks because a key shock absorber was missing.
That's a good way to put it. The push for green energy, while positive in intent, inadvertently removed a critical piece of the grid's stability mechanism, at least during periods of very high renewable generation.
Okay, that's quite a realization. So if we want to keep adding renewables, which most people agree we need to do, how do we fix this stability problem? What are the options?
Well, the analysis lays out a few paths. None are simple fixes, unfortunately. The first one involves batteries, but not just any batteries.
Not like the big grid storage batteries we hear about for storing solar power for nighttime.
Not exactly. Those are typically lithium-ion chemistries, like lithium iron phosphate or NMC. They're great for storing large amounts of energy and releasing it over hours. Slow charge, slow discharge, relatively speaking.
Oh.
What's needed for this problem, stabilizing the frequency wobble, is something much faster. Batteries that can react almost instantly, charging or discharging huge amounts of power in fractions of a second to counteract those fluctuations.
Like a super fast reflex for the grid.
Exactly. And the technology highlighted for this is lithium-titanium batteries. Different chemistry, different properties. They sacrifice some energy density, maybe, but they gain incredible speed and charge and discharge.
Lithium titanium.
Yeah.
Okay, so why aren't we just installing those everywhere? What's the catch?
Well, there are a few big catches. First, manufacturing capacity. While the materials themselves, like titanium, are reasonably available, the factories making these specific types of grid-scale, fast-response lithium-titanium batteries are, well, there aren't that many.
Limited supply.
It's very limited. Zion's analysis suggests that if you took the entire world's annual production of these batteries right now and dedicated it all just to Spain and Portugal, it would take a full year just to build enough to stabilize their grid.
1 year of global production for just the Iberian Peninsula.
Yeah. So scaling that up globally, we're talking about a massive industrial build-out. Think 15, maybe 20 years realistically to get the capacity needed worldwide.
15 to 20 years. That's a long time horizon for such a critical issue. Are there other hurdles? Raw materials?
Definitely. Beyond just the specialized battery manufacturing, there's the lithium itself. While lithium is in these batteries too, the processing of raw lithium into battery-grade material is hugely concentrated.
Right.
Overwhelmingly, yes. So that brings in all sorts of geopolitical risks, supply chain vulnerabilities, not to mention China's own internal demographic and economic shifts that could impact things. Building out diverse, secure lithium processing elsewhere is another massive time-consuming challenge.
Okay, so the high-tech battery solution, while possible, is looking complex and very long-term. What's the alternative? Is there a simpler, faster way?
There is a much simpler, though perhaps less environmentally appealing option discussed. It's basically keep some of the old system running. Meaning maintain a certain baseline percentage of power generation. The analysis suggests around 15 to 20% from traditional thermal plants, coal and natural gas.
Running all the time, even when the sun is shining and the wind is blowing.
Continuously. The key isn't just having the capacity, it's having those large turbines spinning and synchronized to the grid constantly. That ensures there's always enough of that kinetic energy, that flywheel effect, online to stabilize the frequency, no matter how much renewable power is being generated.
So you'd essentially be running some fossil fuel plants, not necessarily because you need their energy output at that moment, but specifically for their stabilizing physical properties.
That's the idea presented. It's a direct trade-off. Accept some level of ongoing emissions from these plants in exchange for immediate grid stability.
A pragmatic, if maybe uncomfortable solution for some. Now, you mentioned Spain and Portugal were particularly vulnerable. Why them specifically?
A key factor highlighted is their geography, or rather their grid geography. They're kind of at the edge of the European grid.
Limited connections to France, mostly.
Right. They don't have a lot of high-capacity interconnectors linking their power grid to the rest of continental Europe compared to, say, Germany.
Ah, so Germany, even if it has tons of wind and solar running sometimes, it's deeply plugged into the grids of Poland, France, the Netherlands, etc. It can borrow stability from its neighbors' thermal plants.
Exactly. Germany benefits from the inertia of a much larger interconnected system. Spain and Portugal are more like an electrical island, relatively speaking. When their internal stability wobbled, they couldn't easily draw on external stabilizers through strong connections.
Which implies this isn't just a Spanish or Portuguese problem waiting to happen elsewhere.
That's the strong suggestion. Any grid that becomes heavily reliant on inverter-based resources like solar and wind and is relatively isolated geographically or electrically faces the same kind of risk.
Who else falls into that category?
The analysis points specifically to places like Australia, New Zealand, and the United Kingdom.
The UK, also an island, electrically speaking, largely.
Precisely, and the analysis even suggests the UK might be more vulnerable in some ways, potentially having less consistent solar and wind resources than Iberia, which could lead to even more fluctuations that need managing.
Okay. One more thing, what about microgrids? We hear a lot about decentralizing power. Do they help with this wobble issue?
Microgrids are interesting. They are smaller, localized grids, maybe serving a campus or a neighborhood. Often they operate internally on DC power.
So no AC wobble to worry about within the microgrid itself.
Right. Within its boundaries, the AC frequency synchronization problem is kind of bypassed. But they come with their own challenges. They're often more expensive to set up initially, and they don't usually have the massive backup capacity of a large interconnected grid if their local generation fails.
So they solve one problem, but maybe create others. And they don't fix the main grid stability issue.
Not directly for the main grid, no. They're part of a different approach, distributed generation. They could play a role in resilience, maybe, but they don't provide that large-scale inertia the main AC grid seems to need when renewables dominate.
Okay, so stepping back, the big takeaway here seems pretty clear. As we push for more green energy, which is essential, we absolutely have to tackle this stability issue head on. It's not just about generating clean electrons, it's about keeping the whole system humming reliably.
Absolutely. It's a fundamental engineering challenge tied to the physics of the grid. And the solutions, whether it's this huge long-term build-out of specialized batteries,
Or making the potentially tough decision to keep a baseline of thermal power running for stability.
or maybe some combination, perhaps including things like microgrids where appropriate. One way or another, something needs to be done to provide that stability function that spinning turbines used to handle. Otherwise, we risk seeing more of these large-scale blackouts.
It really underscores the complexity of the energy transition, doesn't it? It's not just flipping a switch from fossil fuels to renewables. There are these deep systemic interdependencies.
Definitely. Balancing environmental goals, cost, and the absolute need for reliable power is tricky.
So it leaves us, and you listening, with a pretty significant question to ponder, right?
Sure.
Given these challenges, the long timelines for batteries, the environmental trade-offs of keeping thermal plants, the limits of microgrids, what does a truly secure and sustainable energy future actually look like? What compromises might we, as a society, need to accept to get there?
That's the core dilemma, something worth thinking about as this transition continues to unfold.
Indeed. Thanks for breaking that down for us. A lot to consider there.
Yeah.